Hi, I am Lopamudrashen. Welcome back to my channel Electronic Science Tutorial. I will start a new lecture series on NTA UGC NET and West Bengal SET exam for Electronic Science subject. Those who are not follow my channel, please follow my channel. If you like my channel, then please like, share and subscribe my channel. So let's start our class. Welcome back to my channel with a new lecture series on VLSI technology, that is epitaxy. It is very much important topic for you guys, those who are trying to crack NTA UGC NET exam for electronic science, and also it is very important topic for West Bengal SET exam. In Unit 2 of the electronic science syllabus, this topic is placed. In previous class, we discussed about the types of epitaxy and the grown technique or the classification of the grown technique of epitaxial process. Okay. Today I will discuss the vapor phase epitaxy process in detail. Okay. So let's start our class. So here we talk about the in detail of the vapor phase epitaxy. What is vapor phase epitaxy? Vapor phase epitaxy, that means the material transport must be in form of vapor. So you have to use gas reactants and there is some chemical reaction involved. Okay. So you have to use some gas or a liquid with a very high vapor pressure, which can be vaporized very easily. So here we talk about the basic transport process and the kinetics reaction of vapor phase epitaxy. And this is the techniques, or this is the process. The system is very simple. You have a sample holder here. This is the sample holder and this is called susceptor. And you have a few samples placed on top of that. So these are the sample. This one, this one, this one, this one and this one. So these are the samples which you have a few samples placed on top of that. And you have a flow of gas. This is the gas supply path, right? So the gas is actually containing the reactants. The gas flow is controlled by the mass flow controller and the reactants. As they flow over the sample, they react and there will be a deposition on the top of the samples. This process is called vapor phase epitaxy. The reactant material within the gas react with the sample and they deassociate or decompose, and the material which I want to be deposited is formed, and it is deposited on the sample which are already present inside the system. So here is the deposition done, here is the deposition completed. Okay. So I have a stagnant layer, which means I have a stagnant layer of reactants. This stagnant layer is also called boundary layer. So in vapor phase epitaxy process, the width of the stagnant layer or the boundary layer is a very important criteria. Okay. So this is the technical process or this is the techniques of the vapor phase epitaxy. So here we talk about the vapor phase epitaxy process, basic transport process and reaction kinetics. When we start for discussing the fluid machines of the gas flow, we consider the Reynolds number. So, when we discussing about the fluid machines of the gas flow, we consider the Reynolds number, and which is a dimensionless parameter that characterize the type of fluid flow into the reactor, and that is Re equal to V rho dr divided by mu, where dr is the diameter of the reaction tube, V is the gas velocity, rho is the gas density, and mu is the gas viscosity. Right. So into the reactor I have a stagnant boundary layer, and the thickness of the stagnant boundary layer is very much important criteria. So we can consider the thickness of the boundary layer, that is defined by y equal to x dr divided by Re to the power half, where x is the distance along the reaction chamber, dr is the diameter of the reaction tube, and Re is the Reynolds number. Right? So from the figure, the boundary layer forms at the inlet to the reaction chamber and increases until the flow is fully established. Although fully established flows are not always encountered into the short length of typical reactor, it is across this boundary layer that reactants are transported to the surface. So here we consider the flux of the gas. The flux of spices going to and coming from the wafer surface, and these are the complex functions of several variables including temperature, system pressure, reactant concentration, and layer thickness. So the flux is defined as J equal to d dn dy. Okay. So this is approximated as J equal to d Ng minus Ns divided by y, where Ng is the gas stream concentration and the Ns are the surface reactant concentration. D is the gas phase diffusivity, which is a function of pressure and temperature. Right? Y is the boundary layer thickness, and J is the reactant flux of molecules per unit area per unit time. Okay. So under steady state conditions, the flux of reactant across the boundary layer is equaled by a chemical reaction at the silicon surface where the film is growing, and that is equal to J equal to Ks Ns, where Ns is the surface reactant concentration and Ks is the chemical reaction rate constant. Okay, representing the surface reaction. So if we equating the equation 4 and 5, we can determine the surface reactant concentration, that is Ns. So Ns equal to Ng divided by 1 plus Yks divided by D. The quantity D by Y is called the gas phase mass transfer coefficient, and this equation 6 indicates that the surface concentration of reactant, which determine the layer growth rate, is a function both of the reaction chemistry and the gas phase transport process. Okay. So these are the basic transport process of vapor phase epitaxy, and from this process we can calculate the surface reactant concentration, that is Ns. Okay. So here we end today's session. I hope you understand this topic. with this we have come to the end of the session. I hope you like this video. Thank you friends. If you like my video then please do like, share and subscribe my channel. फिर मिलते हैं एक नई वीडियो के साथ. Thank you.